Nothing really is going on in this situation that you haven't seen a million times before, but there is an added complication, which is that you need to think about the reaction carefully at the bottom, whether or not this is smooth. Instead of a peg here, you might have, so basically the situation is you've got a beam and it's on the floor, but it's being held up somehow. So you might have a peg in the wall, you might have like a support here that it's sitting on, you might have a piece of string attached here that's pulled up or pulled up at an angle, all sorts of situations. But we're going to use exactly the same method that we've used in all the other moments problems, which is that we're going to draw a force diagram, all the forces acting on the beam, and we're going to have a distances and angles little thing here separate so we don't clutter up our force diagram. We may need to resolve some forces. We need to be careful that we chase the angle here, alpha, around properly, but then we're just going to do our normal thing. So I've got an example here with a peg. That means that there will be a normal reaction. That's nice. I'm being nice to myself in this example by getting a right angle there. If it was string and not at a right angle, it would be a little bit more tricky. We've also got to put on the reaction. So that's going to have a component going straight up, perpendicular to the surface. And that's the reaction at the base. This is the reaction at the peg. They are different. This is the friction at the base. And if it's in limiting equilibrium, that will be equal to mu times the reaction at the base, where mu is the coefficient of friction between the beam and the floor. Right, we may or may not have some other forces. Maybe somebody's pushing something. We've also got weight, which may or may not go through the centre, depending on whether or not it's a uniform beam. I don't know. So I'd put some things on here telling me all the distances, and I've got the angle measured there, and maybe there's another angle measured here. So sort out your force diagram. You're going to do all the forces up equal all the forces down, which involves resolving this force. Then you're going to do all the forces left as forces right, which involves the resolving of this force, and then individual moments. Now, if I take moments about the base, then this line of action of this force, the line of action of this force go through the base, therefore they don't contribute any moments. The moments are coming from these two forces. And if I'm doing it around the base, which I don't have to do, I could do the moments about anywhere, but if I am doing it around here, then the weight, the perpendicular distance there, is this distance across here, where that's the weight. So the diagonal distance there, if it's a uniform beam, will be half the length of the beam. And then the bit across the bottom, it will be half the length of the beam cosine alpha. So it'll be 0.5 L cosine alpha. And then mg. But obviously that does depend on whether or not it's a uniform plank, uniform beam. So this would give us a clockwise moment, and it would be 0.5 L cos alpha times mg. Where's my other force? Here. Now, don't forget I've resolved this force, but for the purpose of moments, this is why it's really good to do them individually. Just look at the force. Here's the point, the base. There is the line of action of the force, which has magnitude of reaction at P. And then this is the perpendicular distance. It's that distance here, which we almost certainly know. I'll call it D. So this would be an anti-clockwise moment, and its magnitude would be D times RP. Okay, so everything is the same as before. Let's go through this example. Uniform beam, mass 14g, length, uniform, so we know that the weight is being modelled as coming from the centre. There's the length, it's got A, it's on rough horizontal ground. So here is my diagram. Rough horizontal ground means we have friction parallel to the surface, and we have a reaction, of course, at the base. And we've got the weight in the middle. And do we know the mass? Yes, 14. So it's 14g going straight down. What else is happening? There is a peg at C. C is not the end, B is the end. So the peg is like here somewhere, and that's 13 meters up to the peg, and we will have a reaction at the peg. Now this is a very common situation, so I want to show you how to resolve that force at the peg into its components left and right and up and down. So the diagonal is length RP, that's the magnitude of the force, but where is the alpha? Do we even know at 18 degrees? And you have to learn how to sort of chase this around, this alpha. So the alpha down here, you can just memorise that it goes there. That alpha is that alpha. But if you want to understand it, basically if you think of Z angles, we have got in here, that is alpha in there. But this is a right angle. So if that's alpha, that's 90 minus alpha in there. But this is a right angle. So if that's 90 minus alpha, then that's alpha. So you sort of chase the alpha around the diagram, and that allows you to split your reaction at the peg up into RP cos alpha going up and RP sine alpha. You don't have to use RP, you could use whatever you like going that way. And there's your peg. There's the mass, and there's the reaction, and there's the friction. Now we here have, it's on the point of slipping. So this is limiting equilibrium here. So the friction is going to be its absolute maximum, which is mu R, not any old R, this R, RB, and it's mu that we're trying to find. Okay, I'm going to put some distances on this. Alpha is 18. So in this case, actually, I didn't need to put alpha because I actually know that it's 18. And I have got a distance, well, the weight is in the middle and it's 15 meters. So it'll be 7.5 meters up to the point of the weight. And then I've got 13 meters from here to here. So this distance there, that is going to be 13 minus 7.5, which I don't trust myself to do. 5.5. So this whole thing is 13. And from there to there is 7.5. And that's the bottom. And this is C. Right, now that I've got everything set up, I've got my force diagram, which I'll use for the moments, and I've got the distances here to refer to, and that is not cluttering this up. I can use my 3 equations. So equation 1, forces up is forces down. What forces have I got going up? RP cos 18, that's going up, and this one's going down, and that one's going up. That's one equation. Not that I can get anything from that yet because it's got 2 unknowns, but never mind. Equation 2. Forces left is forces right. Left, I've got RP sine 18. And right, I've got mu R. Not any old R. RB, the reaction at the base. Right, let's do our moments. I'm going to do them individually, as always, and I'm going to do it about B, which I don't have to do. Obviously, I can do moments about any point at all. I could do B, I could do the middle, I could do C, I could do anywhere. But I'm going to do B on this one, because that means that these 2 forces, because they're lines of action, both go through B, the base, is what I'm, A. Okay, I was using B for base, but the question's called it A, so I'll call it A, which means these should be A's, which means this is an A, and that is an A. Doesn't matter, I'm just being pedantic. So individual moments about A, how many forces have I got? Well, I can think of it as 2, or I can think of it as 2, this one, this one here, and this one here, or I can think of it as 3, that one, and that one. Now, it depends. If this wasn't at 90 degrees, then I might consider doing that one, and in fact I probably would do that one and that one separately, but because this is at 90 degrees, that distance is really, really simple. So I'm going to do that one and work out that distance, not that I have to work it out because I got told it's 13. So that's going to be a anti-clockwise moment, and the magnitude of that moment is going to be RP times 13. And then the other one, there's the base, and there's the weight, and the perpendicular distance of the line of action of the force to the point I'm taking moments about, this one here, or I'm looking at that. So the diagonal is 7.5. I'm going across the bottom, so I want cosine because it's adjacent to the 18. So this will be 7.5 cos 18 is the perpendicular distance to the line of action of the force. That gives a clockwise moment of 14g times 7.5 cos 18. Now I can set up equation 3. I'm in equilibrium, so the clockwise moments equal the anti-clockwise moments. 14g times 7.5 cos 18 is the same as RP 13. Right, now this one's only got one variable, so I can use equation 3 to get RP straight away. That comes out to be to 3 significant figures, 75.3, and that's in newtons because it's a force. Then I can use this in equation 2. Not yet. I can use it in equation 1 to get the reaction at A. Obviously, I would show my working here and sub it all in and stuff. This is 65.6 newtons. And then I can use these two things in equation 2 to get mu. So to three significant figures, we get 0.355. So long as we haven't done any premature rounding, kept all our accuracy all the way through the simultaneous equations, then you get 0.355. Coefficient of friction does not have any units, so that is your final answer.